Okay, first off, before I get started, are there any questions from 2.5 or 2.4 or 3? Any questions from the homework before I get to 2.6? Okay. I'll wait just a few more seconds before we get kind of going. So 2.6, we've actually done part of 2.6 already. The very first part in 2.6 that your book covers is domains of functions, actually. And I'm going to do like just two quick examples. This is from the last test. I'm going to do just two quick examples, and then we're going to go on. And the reason I'm choosing those examples is they might pop up in examples later on once we get to domain of what we're really covering today, which is composition. Okay, so that's really the topic. But let's look at the domains. Remember, we talked about two red flags for domain. The first red flag, which tends to be more common, this is if I asked you for the domain of this function, is if we had x's in the denominator, right? If I had something like 5 over x minus 3, and I asked you to find the domain, you'd say, oh, well, hey, I've got x minus 3 in the denominator. And it turns out x minus 3 cannot be 0 because it would cause a division of 0. And I solve it out, and you find out that x cannot be 3. Now, to write that in interval notation, which is what we talked about with domains, you would say, look, x can be anything. It just can't be 3. So it could be negative infinity to 3. Got to use parentheses, right? Because it can't be 3. Or 3 to infinity. Okay. Hopefully that's still back there in your brain somewhere, but it was from the last test. So it's just a little bit of a review from this section, actually, the beginning of 2.6. Okay. And then let's do the other one. So the other one's when we had an even root. And so if we had an even root, let's say it was like 2x plus 1. And with the even root, we just had to make sure that whatever is underneath the radical was greater than or equal to 0. So 2x plus 1 was greater than or equal to 0. So we solve this out, subtract the 1. We get 2x is greater than or equal to negative 1, divide the 2. We find out that x has to be greater than or equal to 1/2. Now again, x can be anything as long as it's greater than or equal to negative 1/2. So to write that, you'd use a bracket because we could be negative 1/2. And then it would go to infinity, right? So this would be the domain of this function. So these are the two main red flags. We've got the when an x is in the denominator, and we've got the square root. We should say even root, which is technically the rule, but square root is how we see it pop up more often. Okay, that's just a quick review of the first part. The homework you've done already for it, I've already assigned it from the last test. So now we're going to get to actually new stuff from 2.6. The very first thing your book talks about that's new in this section is the combination of functions. Combination. So when we're going to talk about combining functions, it's really an intro to composition. But combination means we have two functions and we're going to combine them together through some basic algebraic principle, okay? So your book, it's on page 289, guys, if you want to look at where it starts. But it's very, very straightforward. So let's kind of look at it with examples. That's the best way to teach this one. Let's say I've got two functions. Let's say I've got f of x equals 3x plus 2. And let's say g of x equals, let's say x squared minus x minus 6, okay? And there's four basic algebraic functions, or algebraic combinations, I should say. There's addition, subtraction, multiplication, and division. And I'm going to go through each one of those with these two functions, mainly to show you how we notate it. I assume you know how to do the operations already, but to see how we notate this. So if I wanted to add these two together, you would actually write it like this. So this is the sum. You'd say f plus g of x, okay? F plus g of x. And then really all you're doing is you're adding f of x plus g of x. It's very straightforward, nothing too crazy. So for us, it would be, 3x plus 2 plus x squared minus x minus 6. So, you add like terms. Addition's not a big deal. You can just kind of make it go away. You don't have to distribute it through. So like terms, I've only got 1x squared. I can add the x's together, right? 3x minus x, so that's going to give me 2x. And then 2 minus 6, so that's going to be a minus 4. And this would be your answer. So f plus g of x, if you want to add them together, if we need to add them together, you would just have this answer for this example. Now, in actuality, you're just adding the f plus g, okay? Not a big deal. Now, you can throw a number in there, and there's nothing wrong in that, so this kind of turns into like a basic kind of function example. So if we stick with sum, and let's say we had f plus g of 3, okay? And we wanted to know what f plus g of 3 is. Well, really, that's just, if we stick back up here, it's just f of 3 plus g of 3, okay? You put 3 into both of those functions. I'm kind of wiggling on my side. Okay. Well, f of 3, if I plug 3 into here, it's pretty easy. 3 times 3 is 9, plus 2 is 11, right? Now, if I plug 3 into this trinomial, 3 squared is 9, right? Minus 3 would be 6. Minus 6 would be 0. So actually, it turns out to be 11 plus 0. So 11 plus 0, that's just 11, okay? So notice, for this example, these are two different examples. It's kind of like A and B, okay? For this example, we wound up with another equation. It's because we didn't have a value for x, right? So we wound up with an equation for f plus g of x. Over here, we're given a number for x, so we wind up with a number. You're never going to wind up with an x or any variables if you're given a variable to start with, okay? Questions about that? It's not a big deal. I mean, the main question probably should be like, when am I ever going to use this? Well, it really turns, there's a lot of real world examples actually with combinations. A really easy one would be like a revenue function or a profit function, right? If you wanted to find profit, you take revenue minus cost. So I'm going to keep the same equation, or two equations, I should say. So for like difference, this would be the difference. So we've done the sum. Difference would be, let's say we do not order matters for difference, right? I mean, like 5 minus 2 is not 2 minus 5. So we have to be careful on how we order these. So if we wanted to say, if we wanted to subtract g from f, we'd say f minus g of x, okay? And really all you're doing is f of x minus g of x. Not a big deal, okay? So the big deal is going to be the fact that we have to distribute this negative through this trinomial. So f of x we know is 3x plus 2 minus, now g of x though is this trinomial. It's x squared minus x minus 6. So we've got to be careful with this, the subtraction, because we have to distribute the negative to all three parts. So we're going to get 3x plus 2 minus x squared plus x plus 6, right? Once we distribute the negative. So then you wind up with a negative x squared. Now, the x's this time are 3x plus x. So we get plus 4x, and then we get plus 8. So we wind up with the difference equation. Not a big deal, okay? Let's just go down to the next to the product equation. So product, the way you notate this is actually f times g of x. So the product equation, we've got to multiply this binomial into this trinomial. So you got to be careful. You got to make sure to distribute each part into all three parts of the second one. So I'm going to take the 3. I got to multiply it into all three parts. And then I've got to multiply the 2 into all three parts. So 3 times x squared, that's going to give me 3x squared. 3x times, oh wait, no, it's 3x cubed, isn't it? Yep, 3x cubed. 3x times a negative x, that's a negative 3x squared. 3x times negative 6, that's negative 18x. 2 times x squared, so that's a plus 2x squared. 2 times negative x, so it's negative 2x. And then we get minus 12, right, for the last word. So there's 6 terms when you multiply a binomial into a trinomial. But what should happen is we have combination of these. So this turns out to be 3x cubed. Now we got minus 3x squared plus 2x squared. So minus x squared minus 20x, negative 18, negative 2, and then a minus 12, okay? So this would be our FG of x. Pretty straightforward. Now look, let's say that was A. If you already found the equation and the book or the test asks you for a number, so we want FG of 1 to keep it easy. Look, you can, since you already found the equation, you can just plug it into all the terms in the equation. Now, if you didn't do this at first, you could go back and plug it in and find, f of 1 times g of 1. That's fine. There's nothing wrong in that. But since we already found the equation, I'm just going to plug it in. So it's going to be 3 times 1 cubed minus 1 squared minus 20 times 1 minus 12. So 3 minus 1 minus 20 minus 12. So we get, let's see here, negative, so this would be negative 2, positive 2, negative 18, so it's like negative 30 maybe? Is that right? Yep, that sounds right. So we wind up with negative 30, okay? So we get the difference. Be careful because you've got to make sure to get the, you really have to make sure to distribute the negative, okay, with the difference. Multiplication, the product, you've got to make sure to FOIL it out if it asks you to do it long ways. Now, look, if you had f of g of 1, you can do f of 1 times g of 1. It makes the math a little easier. But if you already have the equation, you can just plug it straight in, okay? Questions before I get to quotient? These aren't any, not really crazy or anything like that. Quotient. So now we've got, no, this is quotient. So we've added, we've subtracted, we multiplied. Now we're going to divide, okay? So to divide, let's do, oh, we're still using the same f and g, okay? I'm not going to be lazy. Do it like that. Okay, so we're going to say, what is f over g of x? Now I'm going to tell you, this is typically the easiest, the easiest one. So you just have to do f of x over g of x. So this would be 3x plus 2 over x squared minus x minus 6, okay? Very straightforward. Now, you might want to see if this simplifies. It's not going to. I'll try to find one here in a minute. Maybe that does, but this doesn't simplify. So we're done here. That's it. Okay, that is it. Now, the question that typically follows the quotient question is, what is the domain of f of g of x? Okay, what's the domain of f of g of x? And we're going to find the domain. Look, if we've got to look at this function right here, right? It's a new function. And we just have to set the denominator, not equal to 0, right? We're doing what we did a second ago with that first example. So we just set the denominator not equal to 0. And then, look, we've got to solve this one by factoring, quadratic equation. I don't care how you solve it, okay? You just know how to solve a trinomial. I'm going to factor it. And this factor is actually going to tell me if something cancels up top. So if I factored this, this would factor into x minus 3, x plus 2, right? Negative 3 times 2 is negative 6. Negative 3 plus 2 is my negative 1. And notice that doesn't factor with 3x plus 2. That doesn't cancel. Neither one of these are the same as 3x plus 2. So it doesn't cancel. Like you could write this out like this. Now, you're not wrong in writing it out like this. You factored the denominator. Notice no three parts are the same, so nothing cancels, okay? But let's finish over here. I've got to find the domain. I have to set each one of those not equal to 0. So x cannot be 3. And x cannot be -2. So we have two things now that our x cannot be, right? So if we think about this, the first thing it can't be is really -2 if we go in order. And then the second thing it cannot be is +3. So it's -infinity to -2. We could be anything in there in that interval. Then we could be anything in between -2 and 3, right? And then we can be anything greater than 3. That would be my solution, okay? That would be my solution. Okay, that's fine, Sherry. So any questions about this? We're gonna do some like goofier ones. We're gonna do one that actually like has kind of a real world example to it, because these do have actually a lot of. If we know the patterns going on in the real world with when it comes to the functions of like knowing how much something changes compared to something else, we can really do some neat math, real world math with these two functions. Your book has one. This is example 4 on 291. I'm just going to work it out. I know they work it out for you, but it is kind of neat. It says example 4 says applying the algebra functions. We open the section with the functions that model the number of births and deaths in the U.S. from 2000 to 2009. So they've got a birth function, -2.6x squared plus 49x plus 3994. And they have a death function, -0.6x squared plus 7x plus 2412. Okay, that's 2,412. I kind of goofed up on the 2. Welcome back, Sherry. So now the question states, A, write a function that models the change in U.S. population for the years from 2000 through 2009. Now I'm going to assume, oh yeah, it says that X is years after 2000, okay? X is years after, so like 2002 would be 2. 2012 would be 12. Okay, so X is years after 2000. And then the B and the X, so this is number of births and number of deaths in thousands. So B and D are in thousands. Okay, B and D are in thousands. Okay, so that'll help whenever we're going to kind of explain what's going on. So the question says, though, write a function that models the change in U.S. population for the years. Well, you know, deaths are going to be a minus, right? And births are going to be a plus. So if we wanted the change in population, we would just do B minus D, right? For the years between 2000 and 2009. So we could do, so this would be -2.6x squared. Okay, wait, hold on. I'm going to write this underneath it because it's going to go kind of a long ways. It's going to be -2.6x squared plus 49x plus 3994 minus, now I'm going to subtract off the d of x, so 0.6 x squared plus 7x plus 2412, okay? I'm going to take my calculator out and just add these together. So, hold on. Well, the first one's not bad. -2.6 plus 0.6 is going to be 2, right? That's not a big deal. Now, what's the next one going to be? Hold on, let me write that down. -2x squared. Then we got 49 minus 7. Remember, it's minus because we distribute this through. So if you want to just change the signs here, you can. If you want to say, well, if you distribute, this becomes a plus, this becomes a minus, and this becomes a minus, okay? So 49x minus 7x is going to be 42x. 3994 minus 2412 is 1582. Okay, so this would be my equation for the change in population each year. Okay, that's the change. It's just the births minus the deaths, and that gives us the change in population. So part B says use the function from part A to find the change in US population in 2008. So 2008, change in population. Well, we know X equals 8 because it's years after 2008. So B minus D of 8. Now I can plug it into that equation. Negative 2 times 8 squared plus 42 times 8 plus 1,582. Okay, so for B, you just need to plug in the 8 to that difference function. And if you do that, now I'm going to just steal this from the book because they worked this one already. If you do that, you wind up with 1,790. And remember, it's in thousands, so it's actually millions, 1,790,000. Okay, so that means in 2008, we saw an increase in the population of 1,790 million. Kind of neat. Okay, or I should say, we didn't see that. This is a model of what is predicted to happen or what did happen. So that doesn't mean that's exactly what happened. It's just an estimate. It's as close as we can kind of get formulaically. Okay, part C. Part C says, does the result in part B overestimate or underestimate the actual population change in 2008 obtained from the figure 2.50? I'm going to look for figure 2.50 because I'm not sure what they were saying. Figure 2.50. Okay, 2.50. This is on page 286. On page 286, it says there were, in 2008, there were 4,247,000 births and 2,453 deaths. So if I subtract that, it's just from the graph. I'm reading the graph. 4,247 minus 2,453, 1,000. Hey, that's pretty close. 1,794. So it barely underestimates from the graph. Hold on, I'm gonna see how they kind of said that. Yeah, that's really close. But yeah, it does barely underestimate by like 4,000 people. So not bad. So, but our model barely underestimated what actually happened that year, rounded to the thousands. Okay. Questions about that, guys? It's a good kind of real world example. I'm going to go over these graphically now next. And I'm going to try to use your book because this is kind of hard to graph. Hold on. I think it's in this section. Yeah. Let's look. If you've got your book out, I want you to turn to page 298. I'm going to try to get it on the screen. But again, hold on. If I can just move this over. Hey, there's me. Okay. Hold on. This example right here. That's kind of cool. Okay. That example. Oh, there we go. Let's see if I can get it. There's probably some major like copyright issue. Actually, there's not. This is a fair use for education. I've had to learn about that in this doctorate. Okay. So we've got this example here. Now, do you guys see how we've got the blue line represents f of x, and we've got the green or the red line that represents g of x, okay? And then it's asking us these different questions. So f plus g of -3, f minus or g minus f of -2, and so on. So I'm going to work these, and look, we don't know the equations at all for this one. That's why I'm bringing this up, and I like this question on the test, okay? So if we look at this one, I'm going to do the even one of the evens. Oh, it tells us the answer. I've got the teacher edition, but let's find out how they got it. So find G, this is 84. Find G minus F of -2. Okay. I can kind of, I could do it this way. We want to know G minus F of -2, right? Now look, so this is 84. G minus F, or F of -2. So now I know equationally what that means is I need G of -2 minus F of -2. Okay, that's what that means. So G minus F of -2 is just G of -2 minus F of -2. Not a big deal. But now I've got to look at the graph to figure out G of -2 and F of -2. So my X value is -2 here, right? And look, my X value is right there, okay? And now if I want the G function is this red one, right? So look, if I go to G of -2, the Y value is +2, right? Remember, this is the X value and it pops out the Y value. So if I go to -2 here, and if I look at the red function, I can see that the Y value is +2, okay? Looking over at it. Minus, now F of -2, now F is the blue function, right? So if I look at the blue function, I do the same thing because it's the same X value. So -2 is the X value. I'm going to go up to the blue function. Oh, that's up here at +3, okay? So the Y value for X equals -2 of F is a +3. 2 minus 3, -1. Okay, -1. Kind of cool. I know. Okay. Questions about that? Okay, I'm only going to ask you to do actually these four. I'm not worried about the domain of these and all that fun stuff. I'm not worried about that. It's the 83 through 86 part where you add, subtract, multiply, divide. Okay, you add, subtract, multiply, divide. And I want you to try those. And if they're not making sense, tomorrow and honestly, these are the ones that usually don't. We're going to go over composition version here in a minute. They're kind of the challenge problems. If they don't make sense, we'll go over them at the beginning of class tomorrow. Okay, so now let's switch to compositions. Okay, make sure I've got this going on. Messed with the camera a little bit too much. This is goofy. Sorry, guys. I know. Sorry for getting motion sickness here. Okay, so now let's switch to compositions. It's the other part of this this section. So composition functions are kind of goofy, especially if you've never seen them before. And I really go over, when I lecture on these, I go over kind of real world examples first. And I need you to get ready to like chat, go in the chat bar, because I'm going to ask you if you can think of different examples once I kind of explain what's going on, okay? So let's say, I'm going to start with just the definition. So the definition of a composition is really that you're taking the Y values of one function and you're plugging them into the X values of another. So it looks like this, like F, and we use this little circle, F composed of G. And what that means is you're taking the G function and you're putting it into the F function, okay? So it's not multiplying. It's not like that. It's not like where you take the F times G. It would actually be written like this, F composed of G. So you're taking the G function and you're putting into the F function, and it creates an entirely new function, okay? It creates an entirely new function. So this is where I'm going to pause for a minute on the math. And I think some of you had me before. You might remember this example, but can you think of an example where you put something into something else and it creates a whole new thing, okay? You put one thing into another thing and it creates a whole new thing. So I want you to put it in chat. There are no stupid answers, I promise. I have heard extremely goofy answers, but none were stupid. And actually, I can kind of make an example out of the goofy ones. They're even more fun. So can you think of anything that you would take one thing, you put it into the other thing, and boom, you've got a whole new thing when you kind of compose them that way. I'm going to give you a minute to think. I'm going to make sure my chat's on. Coins into a vending machine. Kind of. I like where your brain's going, Travis, though. Travis, that would be a hard example for me to make kind of in algebra, but it's not the worst. It's not the worst. I mean, that's not a bad example. It's a great example. Yeah. Chastity recipes. There's a lot of recipes that way, where you put one thing into another and it gives you something else. I like Travis's example, but Travis, that's a great example. And if your brain thinks of it like that, you could probably use that to kind of explain it to yourself in a way. Egg, milk into flour, pancakes. Yeah, it makes pancakes, definitely. Oh, yeah, you got to add a little vanilla in there. Vanilla, a little dash of vanilla in pancakes. Perfect. And a lot of butter. Okay, anything else? These aren't bad. I mean, these are really good examples. I'll tell you this, Sherry, I'm not gonna go with your example on that one, because it's not like that example is more like we're mixing everything together and we're making a new thing. I know that sounds goofy. It just doesn't work for my example. It's a great example though, because you're right. You're taking stuff and you're putting it into another. But I mean, if you want to stick with food, usually there's a good food example somewhere. But it's not. I mean, sure, it's not a bad thought. If you want to go on the food track, there's definitely a lot more examples in the food world where you like take one thing, put it into power source. That's not bad. I like that. Yeah, you got the power source, you got the power outlet, plug them in, boom. Current. Yeah, that's not bad. I like that one. I'm probably going to stick to food, Laura, just because that's what I like for my example. But I do like that example. I like that idea. That's more like an addition, though, because you're kind of combining the two things and not like composing it, I think. I think that's how power works. For that example of power, because you're connecting two things. Oxygen to carbon dioxide. Oh, man. It's been so long since I had that class, Sherry. I have no idea. Let's stick to food. I'm better with food. I'll give you an example. Let me. Honestly, I really like all your examples. I do like the idea of carbon dioxide, but the thing is, with carbon dioxide, you're attaching oxygen to the hydrogen, I believe, right? For carbon dioxide, is that no carbon dioxide? I forgot, but it's like there's an oxygen and oxygen. Like I know hydrogen dioxide, right? H2O. You're really combining the two, so it's not really like a composition of the two. Let's stick to one that I know kind of helps students understand, even though I want you to know I do like all your examples in the chat. I really, really do. One of my favorite things when I'm not on this low carb diet, jelly donuts. Okay, jelly donuts. And I know this is goofy. This does not work out algebraically, but the idea is to get the order of these. Order matters with this. Look, that second function goes into the first function, okay? The first does not go into the second. So if we want to make a jelly donut and we know like we've got some function, we'll say J is the jelly, right? And the D of X is the donut. Mouth is watering, this is sad, okay? If I wanted to make a jelly donut with a composition, let's think here. Would I put the D first or would I put the J first? Let's think. Okay, so I've got to put the second one goes into the first one. So yeah, well, no. Think about this. I've got to put the D. Let's do the J first. If I put the J first, okay, what this tells me is I would put the donut into the jelly, which sounds amazing. Like if you cut up donuts, put them into a jar of jelly and have like donut jelly. I I would eat that. I honestly, I'd probably eat anything, but I would definitely eat that. But this wouldn't create the jelly donut that I'm going after, right? Because this would be putting the donut into the jelly. So this is more like donut jelly, okay? Sounds awesome. So we need to do the opposite. We need to do the donut first. Because the donut, and I mean, if you think about a jelly donut, the donut's on the outside, right? And you put the jelly on the inside. So the jelly's going to come second. And we're going to put it into the donut. This would be a jelly donut. Okay? That would be a jelly donut. So whatever is second is going to go into the first function. I haven't done anything algebraically yet, but I'm telling you the algebra part on this is not hard. It's getting the order correct that students in the past typically struggle with. And that's why I make up goofy examples. Jelly donut. I like the soft drink one, honestly. Because you wouldn't put like the vending machine into the coin. You put the coin into the vending machine. Like, so if you kind of want to make that example, Travis, it's not bad. But you would, if you said like C of X was the coin, right? And then V of X was the vending machine. If I wanted to put the coin into the vending machine for composition, you'd say V composed of C, right? And this puts the coin into the vending machine. Now, the other way you'd put the vending machine to the coin, I don't think that's going to happen, right? That's not going to happen. So this would give you, I wrote that wrong, guys. I'm sorry. It's horrible, actually. Yeah, you'd say V of C of X. That's how you'd write it. And that would put the coin into the vending machine. Okay. So now let's look now how to do these kind of algebraically. But it follows the same idea of the jelly donut. Okay. I mean, the order really does follow the same idea of the jelly donut. Like if we looked at kind of a basic one, let's see here though. Oh yeah, no, I'll make one of these up for you. You use compositions all the time. Like let's say we went into a store and we had a coupon, okay? And the coupon gives us, $10 off, okay? C of X equals, now look, I'm gonna say X is the price, okay? X is the price. So and we'll do C of X is the coupon. So I got, let's say $10 or $5, it doesn't matter. Let's say I have a $10 off coupon. So X minus 10, right? So C of X equals X minus 10. Now, of course, if you go to a store and you purchase anything, you're going to have to pay sales tax, right? So we'll do T of X for sales tax. So we've got coupon. And we got tax, okay? And I'm not sure what it is in Mountain Home. I'm going to Google real fast what now, at the moment, what the sales tax is in Mountain Home, Arkansas. If you know it, type it in the chat box. Sales tax. Mountain Home. 9.5%. Probably just going to go with that because the internet's horrible in this room. And I believe you. Yeah, okay. So let's say 9.5%. So sales tax 9.5%. So that means, anything we purchase, 9.5% of it you got to add on top of that purchase, right? Now the easy way to do that, if you've ever had to do this by hand, is just add 9.5% to 1. So it'd be 1.095x, right? So, if we purchase something for, $100, let's make sure it works out right. If we purchase something for $100 times 1.095, yeah, it winds up being $109.50. Okay. So we could take the price that it is. If we didn't have the coupon, we just take the price and then multiply by 1.095, and that would give us the total, right? Now we got this coupon though. Okay, and it's going to give us 10 off. Now think about this. If you go to a store and you buy something, let's say we go to, where do you want to go in Mountain Home to buy something? I know my wife's favorite store, TJ Maxx. Okay, I'm going to TJ Maxx even though they never have coupons. Let's go to TJ Maxx. Taking it to the max. Okay, and we've got to buy something for the dog because that's always something we have to buy at TJ Maxx. and she finds this dog bed, and she's wondering, man, I wonder how much this would be with my $10 coupon with 1.095, or really 9.5% sales tax. And then I'm sitting there with my calculator behind her, and I'm doing, no, I don't do that, but I know I can make an equation for it. So it really, this isn't just TJ Maxx. This is anywhere in Mountain Home if you've got a $10 coupon. But you got to think, if you go to the register, are they going to take the $10 off? They're going to take the $10 off first. Typically, they take the $10 off first, and then you pay the sales tax on the difference. Now, I know sometimes that's not how it works. Okay, sometimes you have to pay the sales tax on the difference. It depends on the item. But for this item, you take the sales tax off the difference. Okay, so once you subtract it, then you take the sales tax. So if I wanted the total amount I'm going to pay, I've got to think, I'm going to take the coupon and then put it in here, right? So whatever my let's say it's $50. Well, I'm going to take the $50 off, 10 off the $50, that's 40, and I'm going to pay 9.5% on that $40, right? I'm going to do this first and then plug it into the tax. So it would look like that. I would take the coupon first, take the $10 off, and then I would do the tax on that difference after we take the $10 off. Okay, so here's how this looks algebraically. Like, okay, so what that really means is T, now I need you to follow on, I'm gonna go pretty slow here. T of C of X, right? Remember earlier, that's what we said, how to kind of work this one out. Now, C of X is defined up here. It's X minus 10. I have to put that in now for C of X. Okay. Then now I can find T of X of 10. Look, T is right here, 1.095X. Well, if X is X minus 10, this would be 1.095 times X minus 10, right? Because our X now is X minus 10. Now notice, you don't have to do all this if you realize which one's the inside and the outside function. Since the C is the inside function, all you're doing is taking that C of X and you're plugging it into the X for the outside function, okay? That's all you're doing. If I didn't teach this part, the math gods would shun me, and I don't like that, so I have to teach this part. But realize all you're doing is taking the inside function and putting it into the X of the outside function, okay? Now I'm going to distribute this, so I wind up with 1.095X minus, now 10 times 1.095X would be 10.95, okay? So this is the equation for buying anything in Mountain Home if you have a $10 coupon. So I'm going to say if I go to TJ Maxx and I've got a $10 coupon. Now I know there's no coupons at TJ Maxx. I've shopped there enough. Okay, but let's say we do go in there and we do find a dog bed for $50, and I want to know just an equation to plug it in. This is how all this stuff's programmed in those. Whenever you go to check out in the register, this is how the registers are programmed. Okay, so you just plug in $50, 1.095 times 50 minus 10.95. So you'd have 50, let me get calculator, 50 times, 50 times 1.095 minus 10.95, 43.80, okay? 43.80. Any questions? Now I'm going to check myself because I know how to do it. Look, you take $50, you subtract 10, so 50 minus 10 is 40, right? I'm just doing this on my calculator, times 1.095. Oh, no, times 1.095. And notice you equal 43.8. So instead of having to go through those two steps, you've just got it in one equation, okay? Instead of going through those two steps, you just do it in one equation. Very straightforward, okay? Now, I know what you're thinking. Oh my God, I don't care about this real world crap. I need to kind of get some examples going on with composition functions. And we'll do more of this stuff, okay? We'll do more of this stuff. But I want you to realize, hey, this composition stuff is kind of used in the real world. Now, not algebraically, it's used for a lot of goofy stuff, but algebraically it is used for any kind of two-step kind of equations in a way. Okay. So let's look at one that's just algebra based. So no real world stuff, just algebra, okay? I'm going to steal one. Let's say I'm going to steal from the homework. Yeah, this is number 52. 52 is asking a lot of stuff, actually. So it gives us our f of x is 3x. This is on page 298. F of x is 3x. And g of x is x minus 5. Okay? Now, there's an A, B, C, and D. And I'm going to go through all three or all four of these for this example. So A asks, what's f composed of g of x? Okay? What's f composed of g of x? Now look, if you want to go the long route, that's fine. But really all we're doing is taking the g function and plugging it into the f function. Okay, I'm going to change colors up because I'm going to go the other way here in a second. All I'm doing is taking the g and putting it into the f. So all I'm doing is taking this g function and I'm putting it into that x value for part A, okay? For part A. So I'm going to follow along with that. So that's just equal to 3 times x minus 5, okay? Now distribute the 3. And you wind up with 3x minus 15, okay? 3x minus 15. Any questions other than, man, I'd really like to see that again. Or maybe just see it reversed. That's what I'm about to do. Okay. So I'm actually going to do part B. Yeah, part B next. So B, they flip it. They say, what about g composed of f of x? Okay. So g composed of f. Now we're still the same f and the same g, but for this one, f is going into the g function. So it's the opposite. This is the color I should have used earlier for the jelly donut. I got purple. Okay. I think that looks like blue. But we're going to take now the f function, okay, and we're going to plug it into the x value of the g function. We're going to take the entire f function. It's going to become the x value of the g function. So this becomes 3x, because that's the x value, minus 5. Okay, well, that's it. 3x minus 5. We can't go anywhere else. Can't add the 3x to the 5. We're done. Okay. So we put the f value, this 3x, and we put it into the x. Now, if there were multiple x's, we'd have to put it in multiple x's, and vice versa, okay? But that's just how it is. Now, C and D bring up numbers. So C says, what's f composed of g of 2? Now, look, I've already found f composed of g of x, right? That's this order. It's 3x minus 15. So all I have to do is plug that 2 into 3x minus 15. Okay? This winds up being 6 minus 15. So negative 9. Okay? It winds up being negative 9. And then part D, they flip it around on us. Yeah. Well, what's g composed of f of 2? So now it's backwards. And again, just like before, I've already found g composed of f. It's 3x minus 5. So this would be 3 times 2 minus 5. 6 minus 5. Ooh. Okay. Questions about that, guys? Comments, concerns? I'm going to give you guys, I'm going to steal another homework problem, and I want you to try it yourself just to kind of see where you're at. Like, and I'm not going to go too far down from there. Let's do 54. 54 has the same exact f or a, b, and c, but the f of x is 5x plus 2, and the g of x is 3x minus 4. So it has the same a, b, and c. A, they want you to find f composed of g of x. B, they want you to find g composed of f of x. C, they want you to find f composed of g of 2. And D, they want you to find g composed of f of 2. Okay, I want you to try those. I'll give you a little bit. Try those. Ooh. Okay, I'm going to start going through these. If you don't have them done, that's fine. It's not a big deal. Just kind of follow along, make sure we've got the same stuff going on. So for the f composed of g, so I'm going to take the g and put it into the f. So here's the g function. I'm going to put it into that x value. So I get 5 times 3x minus 4 plus 2. Notice the f function is composed of the g function. So we're putting this into here. That's where it comes from. So I got to simplify it out. So distribute the 5. Wind up with 15x minus 20 plus 2. So I wind up with 15x minus 18, right? Okay, so now let's do that one. So now we're going to take the f function, and I'm going to put it into the g function, right? F goes into g. The second goes in the first. So this winds up being 3 times 5x plus 2. So this is 50. Oh, wait, I forgot the minus 4. Minus 4. So I get 15x plus 6 minus 4, 15x plus 2. Right? 15x plus 2. So if I take the f function and I plug it in, I multiply the 3 and the 5 and the 3 and the 2, and then have the minus 4 left over. Okay, so now the last questions, though, we're okay. Let's plug in 2 and 2 to both of them. So f composed of g, that's up here. So we wind up with 15 times 2 minus 18. So 30 minus 18, that's 12. F of g of 2, well, I've already found f of g, or I'm sorry, g of f. So it's going to be 15 times 2 plus 2. So that's going to be 30 plus 2. So 32. Okay? Questions, guys? I'm going to kick it up a little bit. I'm going to do one example actually before I kick it up a little bit. That's just a little different. And we can't really think of it like this. We have to think of the algebraic way of going about these. Okay, hold on. I can kind of do it with this example. Let's keep the same. Kind of move it up. No, it's right on the edge there. Let's keep the same f and g, but let's do e. Let's say I wanted to know what's g composed. Oh, never mind. I lied. Hold on. Let's do a whole nother one. I'm going to make up one. Let's say we've got f of x equals x squared minus 4, and g of x equals 3x plus 1. Okay? And I wanted to find here, I'm going to do 2 of these. I want to find f composed of g of 2. Now look, I haven't found f composed of g of x. And if you haven't already found f composed of g of x, there's another way of going about solving for this composition with a number. You don't have to come up with the formula if you're not asked to come up with the formula. I just want to kind of show you how to do that algebraically, okay? So the way you would do this actually is you would write it where that g only goes to the f. So it looks like, or I'm sorry, that 2 only goes to the g. So it would look like this, f composed of g of 2. So this can be written like that, okay? And from here on out, we're going to just follow, we're kind of going to work inside out actually, but we're going to follow this down. And the first thing we're going to have to do is find g of 2, okay? We're going to find g of 2. Now, I know g of x is 3x plus 1. So g of 2, I would plug it into this. So I'm going to do this kind of on the side over here. G of 2 would just be, now 3 times 2 is 6 plus 1. So g of 2 would be 7, right? You guys see that? So now I've got to plug that back in. So this becomes then f of 7, okay? Because my g of 2, I found out from this equation, was just 7. Now I just need to find f of 7. I know how to do this. We've done a lot of examples like this one. You just plug 7 into the function. So it's 7 squared minus 4, 49 minus 4, winds up being 45, okay? So it's a little different in that if you start with a number and you don't have the equation already for the composition, you could just plug that number into the inside function. It gives you, whatever you get for that number. So g of 2 becomes 7. And then you plug that 7 into the outside function. And now notice, for the g function, that 7 is a y value, right? That's my x value. That's my y value. So the y value of the inside function becomes the x value of the outside function, which is really kind of goofy, but that's the way compositions work, okay? That's the way compositions work. So if we looked at another one, let's say, I want you to try this one. Let's switch it up. G of f of, let's say 3. g of f of 3. You try that one. So don't worry about finding the equation. I just want you to do this with the kind of formulaically right there where you just plug it in. Okay, so let's try this one. So I'm going to write it like this. G of f of 3, right? Now I've got to find f of 3, so I've got to go to this f function. So I'm going to write that over here, f of 3. Be 3 squared minus 4, 9 minus 4, so I wind up with 5, right? So then I would have g of 5. Over here, g of 5, and I'd have 3 times 5 plus 1. 16, okay? G, 3 times 5 plus 1, 16. Okay. Not too bad. Not too crazy. But I need to go over it. Okay. Questions? Okay. So now I know you could easily accuse me of doing the easier ones for this section. I might come back. If I can finish this last example, I'll go back and work a harder one. But realize when you get to the homework, it's going to be kind of crazy. Or actually the last two examples. So now we're going to go backwards. Let's say I gave you h of x, and it was, let's say, 4x minus 1 squared. And I tell you that h of x is a composition, and it turns out it's f composed of g of x. Okay? H of x is just f of g of x. So I need you to look at this, and especially if you're going to go on to a calculus class, a business cal or a cal 1, you're going to need this in the tool bag, okay? And what you're doing is you've identified a composition, and what you've got to do is identify the inside and the outside functions, okay? You've got to identify the inside and the outside functions that create the composition, okay? So I'm going to kind of write this. We kind of know f composed of g of x then equals 4x minus 1 squared, right? So my inside function, I need your brain to kind of see this. The inside function is this 4x minus 1. So I'm going to write that as g of x. Okay? And if my inside function is 4x minus 1, I need to think of what do I need to put it into to give us 4x minus 1 squared? Well, look, this would be my f of x, right? I would just need x squared. Look, if I gave you this question, if f of x equals x squared and g of x equals 4x minus 1, and I asked you to find f composed of g, you would take 4x minus 1 and you put it into x squared, and you would get this composition. Okay, so here's our two answers then. That's what we're going for. Okay, that's what we're going for. F of x is x squared, and g of x is 4x minus 1. Okay, so let's do another one. Same thing though. H of x equals, let's say, the square root of x plus 2. And we know that it's a composition just like up here. I want you to find, so f composed of g of x equals h of x. Now I'll give you just a minute. I want you to find f of x, and I want you to find g of x. Question mark. I want you to find f of x and g of x. So I need you to find the inside function. I need you to find the outside function. These don't last long, really. I mean, it's more about identifying. So let me think about this one. To me, when I look at this function, the inside looks like that right there. Okay. So to me, it looks like x plus 2 is the inside. And if that's the inside function, I would plug it into a square root function, right? You guys see that? So x plus 2 goes into x, and it would give me this function. So this would be my two solutions, really my two answers for this. They're asking for f of x and g of x. Okay. Okay, I got to kind of rush these last few things, and I'm sorry about rushing, but that's just part of it. So now I want you to real quickly, we're going to go back to our book down here. Sorry to give you motion sickness. And we're going to look at this other graphing example. Yeah. Okay. And we're going to do the same thing, but now we've got compositions. So I'm looking at like 92 here. There we go. 92. Because I know you don't have the answer. You can write down the answers, but 92. 92 says, I want to find f composed of g of 1. Now notice on 92, there's no equations here. Again, we have graphs, right? The blue graph is f. The red graph is g. So if I want to find f composed of g of 1, I need to actually write it like we were just talking about. So it's going to be f composed of g of 1, right? And I need to find g of 1 from the graph. So let's see here. If I go to x equals 1, so x equals 1, right? I go to x equals 1, and now the g function is the red function, right? So I go to x equals 1, and I go down, the y value is -5. So I'm going to write that down over here. So g of 1 just equals -5. I know there's no real organization, but it's hard to write right this kind of corner. So this would be -5. So then I would have f of -5, right? Now I've got to go back to the graph now. But now my x value is -5. So if I go back to the graph, and I go to an x value of -5, but now I'm trying to find f of x. I'm on the f function up here, right? If I go to -5, the y value here would be a +3. So this winds up being 3. And I know I'm right because my answer says it right there. Okay. I wanted to get that example in before. I know this is a hard one. I know this one might just make your eyes kind of cross. I get that. But I want you to try it, and that at least gives you an example when you get to that section. Okay. So let's look at one more. I've got you for about 10 or 5 more minutes. Yeah. I think that's about it. You're going to see some harder ones kind of towards the end with those compositions. I want you to try them. Okay, just try them. If you don't get them, that's fine. You can ask me in class. That's what I'm kind of hoping for. So for homework, now look, you've already done the first part of this homework. So we're going to start on 31 and go through 31 through 43. And the compositions 51 through say 63. These are all going to be odd. And then I want you to flip, actually, hold on, those might not. These are odd. But then the last ones, I want you to do all of them. So 75 through 86, do all those, and then do 91 through 94. And hold on, let me see here. Yeah, I'll dig some odd ones out. So 97, 99, and 101. Those are the applications. So here's the homework. It's on page, starts on page 297. It's section, again, 2.6. Okay, section 2.6. Okay. Do you guys have any questions before I let you go? I'm going to give you a minute. I mean, you still have about 3 more minutes before class ends. If you are done, you can just log out. I'm going to stay on here for 3 more minutes, messing around with YouTube.